Okay, well, let's get started as we always do by talking about privacy, and specifically about what it means to be anonymous. So, given a data set, an individual is anonymous in that data set if you can't answer the question which entry in the data set corresponds to that individual, or you can't answer the question, is that individual in the data set at all? So you're stumped, right? You've got some data, but you don't know if Bobby is in the data. Maybe Bobby is, maybe Bobby's not. It's hard to say. Can you be perfectly anonymous? That is, if we take a subset of the records, or maybe even look at a single record, can we identify that individual? So there's two ways to look at it. I've got a big data set and I ask the question, is this person in it? And if so, which record is theirs? And if I can answer that even with like a fairly high degree of probability, then I've potentially exposed some information. Suppose I'm only 80% sure that a particular row is this person. It's still pretty good, right? I mean, that's still destroying a little bit of the anonymity. Another way to look at it, instead of asking if a particular person is present in the data set, is to look at the data set and say, can I identify a person in the data set? So I take a record out of the data set and say, can I reverse this record to a particular person? And, if I can, even again, probabilistically, then I've destroyed some of the anonymity in that data set. And so in general, maybe not. Probably not, right? Give me enough information and enough truthful information, right? If my data set's lying to me, okay, well, maybe I don't know. But give me enough truthful information and I can probably reverse that to a particular individual or find out if a particular individual is in that data set. So we introduced the concept, we try to formalize this by introducing the concept of quasi identifiers. So what's a quasi identifier? Well, these are attributes in the data. So you can, think of the data as tables and the columns as features or attributes, whatever you'd like to call them. But a collection, let's say, of features in the private information stored in the database that can be used for linking with external information. Remember the trick that our evil villain, Dr. Sweeney, played to expose our hero, the governor. She linked information from the data set, about public employees using healthcare, to information that she knew about the governor, to information from the voter registration database, and through that was able to expose his records. And she just exposed them to him. She just sent them to his office. But even so, that broke the anonymity of the released data set, and that's a problem. We don't want that. So information that's in a data set that we can link to other data sets to find out who you are, those are quasi identifiers. And Sweeney there is, of course, our doctor, who's referencing some previous work by Delineus. So let's think about quasi identifiers in a more formal way. I've got a set of entities, you. You is my collection of people, let's say, that I'm going to talk about. It's the population of my state, or the population of the country, or any set of that I'm interested in. Doesn't have to be people, but let's, for the sake of argument, assume that it is. And I have an entity-specific table, T, which has these N attributes. And it could be anything. It could be age, address, phone number, social security number, what have you. But it's a set of attributes. Okay. Now, clearly, I can take a person out of you and build an entity-specific table for that person. Right? I'll write in that person's age, that person's name, that person's address, their zip code, their birthday, their telephone number, the name of their first pet, whatever. Okay? Doing that, taking a person out of you and producing this row of the table is what f sub c does. Right? F sub c takes it creates a mapping from u to t, so it takes a person and creates the row for that person. I could also have an f sub g, which takes a row, okay, a row, and produces u prime. Okay, u prime is some other set, right? So I come over here, you give me a row, and I produce a person based on that row, or f sub g tells me who a person is based on the content of that row. And notice that I say u could be a subset of u prime. Why would I do that? Well, this allows me to, come in here, grab a particular row, and maybe produce the wrong person. So, what do we have? We ultimately want to define a quasi identifier. We have a set of people, we have rows, we have a function that takes people and produces rows, and a function that takes rows of attributes and produces people, or produces a person. We call q sub t a quasi identifier, and it's a subset of the attributes, right? So here are all our attributes, a1 through an, that we had up here for our table. And we only pick some of them, ai, aj, right? This doesn't need to be inclusive, right? We might pick a1 and a5 and a6 and a19 and a26, and that might do it, right? So it's some subset of the attributes. And we pick this subset such that a particular thing is true, and that particular thing is those attributes allow us to identify a particular person. Here's how this works, right? F sub g is our linkage, right? F sub c converted people to our database. F sub g is perhaps uses another database. It's our linkage that takes rows and hours and maps it to people in that other database. Okay, that's why they're different U sets. Okay. So there's a person, P sub I, and when we take P sub I and we apply F sub C, this gives us the row of the table for that person. We then select out just those attributes. So this selects the attributes for P sub I that form the quasi identifier. And then I apply my linking to it, and I obtain P sub I. So notice I have encoded P sub I into my database, and then using a subset of the attributes, which could be all of them, right? Equality is allowed here. Using a subset of the attributes, I have been able to use my linkage to produce P sub I. So I encoded P sub I, but I was able to come along later and discover that P sub I was in the database. So the example here is if V is a table of voters, a quasi-identifier for V might be name, address, zip, birth date, and gender. That's probably enough to identify a particular person. Name alone is probably not. There may be several John Smiths living in your neighborhood. Address is probably not enough, right? Several people may live at a particular house. Those two together might do it, or they might not, right? You might have John Smith Jr. and John Smith III and so on. Zip code, that probably gets you really close, but address might include the zip code, or it might be separate from it, depends how it's stored. And birth date. Okay, now, do I name both of my twins John Smith? Probably not, but I guess I could. And gender, oh, they're both male. Now we're really in trouble. So, but you get the picture, right? This gives you a lot of specificity. The basic idea is that a quasi-identifier allows linkage attacks on database privacy. You can try to identify which attributes are sensitive for linking, but you might get it wrong and release data which is less anonymous than you would like. How anonymous would you like it to be? So anonymous that no one sues you. right? So anonymous that the FTC doesn't come after you. So anonymous that your personal information isn't exposed by the database. You would like there to be some anonymity. Can we formalize this? We formalize this with the idea of group indistinguishability. We touched on this earlier when we talked about anonymity. Suppose we take a group of records from our database, and that group contains our person of interest. If the individual blends in so well with that group that they're indistinguishable from it, then that's great. That's what we would like. Okay? We give you a set of features, that has to be all of them, right? It's some subset of the database columns, features, attributes, whatever word you like. And given those, the individual is indistinguishable from others in that set. There's not enough variation for you to tell who is who, right? One of these ducks over here is Sammy, and you're like, which duck could it be? Trick! It's none of them, because they're not ducks. Okay? So there you go. So k-Anonymity is what we're describing here. So, more of this notation. D is a database. Q is a set of attributes or features or what have you. D with the Q sub D in square brackets is selecting out just those particular attributes. We did that back on this slide where this gave us a particular entry, a row, and we just selected out the things that were in Q sub T, just those particular attributes. We're doing the same thing here. We're taking the entire database and we're just selecting out the particular attributes that are in Q sub D. So we say this represents the projection of the quasi identifier Q sub D onto database D. A lot of words there. We let D, Q sub D, R denote the projection for row R. Okay, it's just notation. Don't get too hung up on it. The values for the feature of Q sub D for R in our database D. We say two queries. These two queries are indistinguishable if and only if they produce sufficiently close values that we cannot positively say which row is which. Okay? Now, typically, you may require equality. But I talked earlier about how maybe if I can be like 96% sure, that's probably good enough. If I can be 80% sure, that may be good enough. Okay? It just depends upon how much privacy I want in here. It's one of the reasons why, when we get back to it, differential privacy has so much to offer. But for right now, stay with this. We're building to something with this. So k-Anonymity. So two queries, looking at row 1 and looking at row 2, and just the things that are in our quasi identifier in the database. They produce sufficiently close values that we can't say which row is which. And so we write that with a little tilde here. It's not always written this way, but this is how I'm going to write it, because I don't necessarily think that probability 1 is needed. So I don't think you necessarily have to have equality. So I want to say that these two are very similar, and they usually use this for similar. So they're similar enough, I can't tell them apart. They look the same to me. A dataset D satisfies k-Anonymity for some integer k greater than 0, right? What would 0 anonymity be? It wouldn't be anything, right? What would that even mean? We'll see what that means in a minute. If and only if for all rows R in D, there exist at least k minus 1 other distinct rows that are indistinguishable from it. This is from Sweeney, our villain from the last lecture. So he's extremely smart. You'll find her name all over a lot of privacy work. He's a really, really smart person. So what's happening here? k-Anonymity says you give me a row, and I can give you k minus 1 other distinct rows, other different entries, and you can't tell them apart from your row. Right? They all look the same, right? 1 looks like 2, so on and so on. Looks like k minus 1 looks like the original row. So if k is 0, this becomes -1. That makes no sense. But if k is 1, it becomes 0, which means that every row is distinguishable. So 1 anonymity is what it sounds like, right? You are the largest anonymous set I can construct. That's terrible. That's no anonymity. 2 anonymity is better, right? I can distinguish up to pairs, but I can't do better than that. 3 anonymity is even better. 4 anonymity is still better than that, and so on, right? The larger the value of k, the more anonymity is present in the data set. Can we cause our data set to satisfy k-anonymity? Well, we could, naively do it by just duplicating each row k minus 1 times. So instead of having, 1 entry for Alia, I'll have 16 entries for her. Well, that's silly. It doesn't actually solve the problem. That's missing the point, right? And it doesn't really actually satisfy what we really want. Those rows are only distinct in the most technical sense of the word. They may have different indices, but otherwise they're the same. So we really need some other way to do it. How do we do it? Well, typically we generalize the data set. That is, we fuzz the values a bit. We don't add random noise to them necessarily, but we do modify the values in our data set so they are less specific. So instead of saying this is a 35-year-old woman, we say this is a woman age 30 to 40. And suddenly we have information, but it's less specific information, right? So we might bend the data. We might say, this person lives in Illinois, and we don't get any more specific than that. We might report the zip code minus the last couple digits. We might round things to the nearest 10 or do something else that makes sense. Typically, what you'd want to do is look at your data, see how it's dispersed, and then choose your partitions. Choose your partition such that each block of your partition has a fair number of entries. Okay. Now, so we begin to blur the content of our data set. And in doing that, we hope to achieve k-anonymity. But how do we know if we've actually achieved it? Well, we can check. So we grab every row, and for that row, we run a query with the feature subset we care about, okay, the one we think we can link, and we count the rows returned. And the minimum number we should get back is k. Okay, maybe we do this for every single row. Maybe we have some kind of a clever algorithm where we only have to check certain ones. Whatever, right? This should be reasonably fast. N log n, maybe n squared, but it should be less than n squared, right? You should have to check. You check 1 against everything else, then you check 2 against everything past it, and 3 against everything past it, and so your n is going down each time. It should be fairly fast to check that and determine that your database satisfies k-anonymity for a particular k. Okay, so how do I know what k to choose? Well, what I might do is set my k to something like, if I have like 1,000 entries in my database, I set my k equal to 1,000. And I run a query for the first one, and I get back 60 entries. Okay, I know that k can't be larger than 60. So I set my new value of k to 60. Then I run it for the second row, and I get back 42. Okay, now I know k can't be greater than 42. Then I run it for my third one, and I get back 90 entries. Okay, well, k remains 42. And so as I walk through it, I keep my k at the smallest number for a particular query. And when I'm done, the resulting k is the k for my k-anonymity. And I could then ask, is that enough? Is that k large enough? And if it is, great, I can release the data set. And if it's not, I need to change my bins or do something else to my data so that I'm able to release it with sufficient anonymity. So another problem pops up here, which is, what if your data set contains outliers? So outliers are those entries that are so far out of bounds that it's pretty clear what happens, right? If you've got a 112-year-old person in your data set, there just aren't that many. And I know who it is, and I can find that person pretty easily. So outliers are a problem. And you may wonder, how do we solve them? Well, it turns out there is a complicated mathematical theory that we can apply to deal with outliers in a data set, and that is the theory of deleting them. So we delete them. We delete outliers. If you check your data set for k-anonymity and you find that 3 rows take your k from like 17 down to 1, then you drop those 3 rows, right? So if you know, everything tells me my k-anonymity is, let's say, 70. Except for these 10 rows. When I run those 10 rows, my k-anonymity drops down to like 2, or maybe even 1. Well, I want to drop those rows. If I drop those rows, then I can release with a high anonymity, and that's what I want. So clearly k-anonymity is going to work better for large data sets, right? My k can be larger if my data set's larger, right? K can never be larger than the size of your data set. So a larger data set means you can get a larger k, right? It's easier to disappear into a crowd than it is to, disappear into a small room with like a few people, right? People are going to know if you're there, right? It's easier to find Waldo on the cover of Where's Waldo than it is to find him in the giant 2-page spread inside. Just the way that it is. Okay. Let's compare what we know about k-anonymity to what we know about differential privacy. K-anonymity is a property of a data set. Okay? I didn't add noise to the data set. I generalized it. I binned my data, but I didn't add any noise to it. I can release the data set. I can give you the data set, and that's fine. The data set has anonymity built into it. What about differential privacy? Differential privacy is not a property of the data set. If I give you the data, I don't give you any differential privacy with it. Differential privacy is a property of an algorithm. It's a property of the way I let you query, or the way that I record the data. Right? It's not a property of the data itself. And instead of generalizing the data for anonymity, I add noise to the data for anonymity. And those are different things, right? Binning the data is one thing. Adding random noise to it to move the data around, that's different. So let's switch gears. Now we talked about k-anonymity. Let's talk about differential privacy. So let's define some stuff here. Let's let D and D prime be 2 distinct data sets. So something in D and D prime is different. We say D and D prime are neighbors if that difference is limited to a single row. So one row is different between D and D prime. Maybe there's a row present in D that's not present in D prime, but everything else is the same. Or maybe there's a row present in D, but the entries in that row are different in D prime, but all of the rows are the same. Okay? Now, let's let f be a function that takes a data set and returns a value. What would take a data set and return a value? Well, that would be a query, right? A query would do that. We say f is a differentially private function or a mechanism if and only if for all neighboring data sets x and x prime and for all possible outputs s, this holds for some epsilon greater than or equal to 0. The probability, okay, of our differentially private mechanism or our specialized query function applied to x returning s is no greater than the probability when it's applied to its neighbor returning s given this constant. So e is the usual base of the natural logs. Epsilon is some real value greater than or equal to 0. So clearly, as we let this value get large, we're going to allow this difference to become significant, right? If we choose our epsilon to be 0, then this is 1. This term goes away, and we're saying the probability of seeing this is no greater than the probability of seeing this. If we choose it to be such that the result here is 2, then this has to be less than twice this, and so on. So this conditions where we allow these choices to be. The parameter epsilon we can think of as a knob that we can turn to control the degree of privacy, and it's called the privacy budget sometimes. Some publications will call it the privacy budget. Some will call it by different names. We'll probably use a few different names here. But basically, the epsilon here is the epsilon in epsilon differential privacy. Just like k-Anonymity. K was the amount, right? Bigger k was better. For epsilon differential privacy, you want smaller epsilon. You usually want epsilon smaller than 1. Okay? And in general, when it's bigger than 10, we can't really guarantee any privacy. The choice of the specific epsilon, well, it depends, right? We don't know how to tell you specifically how to choose it. It's one of those things where we set a threshold because it seems to work well. Often you'll see 0.1 or sometimes 0.2. I've seen smaller values than 0.1, but it can be all over the map. So, in general, the way we implement differential privacy, the way we create that f function that we call a mechanism, is that we add noise. So we take what would otherwise be the correct clear value, like 17, and then we add some noise to it. And how much noise do we need to add? Well, let's say that the answer is 17. Maybe I should return the value 17.1. Maybe that's good enough and you can't distinguish it. Maybe I should return 19. Maybe that's what I need to return to be good enough that you can't distinguish it. Remember, the original idea was I can't tell which of the different rows that it is. Okay. So, for instance, suppose you ask a census data set for the number of people who identify as Hispanic in Tennessee who are over the age of 40. It's probably a fairly large number, and you won't necessarily reveal anything interesting, and so we don't have to add that much noise. If we get much more specific, if we pick, say, Coffee County, which is a county in Tennessee, south of Nashville, and we pick a more restrictive age, right? Above age 40 could be a lot of people, but below age 10, probably a lot fewer, we might get information that could be problematic, and so we should certainly add some more noise to that result. Some functions are sensitive to changes in ways that others aren't, right? So think about this for a minute. The function we are using could be something simple like counting. Tell me how many people in Coffee County identify as Hispanic and are below age 10. Or it could be, tell me the average age of people in Coffee County who identify as Hispanic. All right? Those are different questions. And a small change in the data set will result in a different degree of change in the result. And so our noise that we add to obscure it has to be different for those two cases. I hope that makes sense, right? If I add another person to my data set, then at most, the output of my counting function goes up by 1. How about my average? Well, my average, as my data set gets larger and larger, my average changes less and less for adding a particular person. So for my counting function, I probably always have to add about the same amount of noise, because every person changes it by the same amount. But for my average, I probably have to add less and less noise as my data set gets larger, because each individual contributes less to the average. We call that the degree to which a particular individual contributes to the overall result, the sensitivity. And it makes sense to call it that. You think of the sensitivity as a function as the amount by which the output changes when you change the input. And so that's what's happening here. And so our sensitivity tells us something important about how much noise we have to add. So now we have two things that tell us about it. One, we have our privacy budget, our epsilon, okay? But then we have our sensitivity, which is specific to the particular thing that we're computing, particular to the average or the counting function or whatever. Now, the mechanism we're going to use to add it in class and in the homework, and there are many different mechanisms, but a very common one, and the only one we're going to really dive into here, is Laplace noise. So we could use Gaussian noise. Gaussian noise would look like the Gaussian distribution. And what do I mean by noise? Well, my correct result, right? So let's say the correct average is 17.5. That is the signal. But I want to obscure that signal a little bit, so I add some noise so that it's more difficult for someone who gets the result to uncover the specific signal. So I add a little bit of noise to it, and that noise looks like adding a random value. That's what noise looks like. And noise comes in many different varieties or flavors, right? So we think about white noise, where we basically have fairly uniform distribution across all frequencies, or we might have noise that's biased toward one end, right? We're adding more low frequencies, or noise that's biased toward the high end, we're adding more high frequencies. And the same thing is true here. And so the question is, what do I use to generate my random noise? Uniform is pretty easy, right? I would just call my uniform pseudo-random number generator and get back a pseudo-random uniformly distributed random value, and I could add that. But that's probably not what I want. And it turns out that for technical reasons that we probably won't get into here, it turns out Laplace noise is a really good choice. Now, if you look up here at the graphs, you'll see it looks maybe a little like a Gaussian, but not really. You see it comes to this sharp point right here. So this red one right, we have 3 of these are centered on 0. So 0 is the mean. Okay, and you see they're symmetric. And this last one, we've shifted the mean down to -5. Then we have this b, which is the second parameter, and b is the spread. Now, you may be wondering, is that the standard deviation? No, it's not the standard deviation. The standard deviation is, I believe it's the square root of 2 times the spread. I don't know why it's done that way. It's just done that way. But it's basically proportional to, it's directly proportional to the standard deviation. It's the standard deviation times a constant. I think that's the square root of 2. And so as this goes up, the standard deviation goes up, you would expect the curve to spread out more. And since there has to be more mass over here, you expect the peak to go down. Right? So you just sort of squishes it. So the second parameter is the degree to which we squish it. And so if we generate a random value from the red distribution, we would expect our random value to typically be right here, right around 0, very close to it. Okay? It could be out here at 6. The probability of generating that is low. Probability of generating 0 is very high, but the probability of generating things close to 0 is also pretty high. For blue, probability of generating a 6 is much higher. And so we might get some 6s or 8s or even 10s, right? And so you can see we can control what kind of values are generated. So what we're going to use is Laplace noise with a center at 0 and a scale, that's the second parameter, that's proportional to the standard deviation, of s over epsilon. Now what is s? S is our sensitivity, right? This tells us how much we need to account for the function, right? Again, remember the sensitivity for the average was getting smaller as we added, was getting smaller as we added more entries because each entry changed it less, and so we needed to add less noise. So a smaller sensitivity means add less noise. Okay. Alternatively, a smaller epsilon means add more noise because, right, epsilon is our privacy budget, and as we make it smaller and smaller and smaller and smaller, we need more and more privacy. So our result needs to be directly proportional to our sensitivity and inversely proportional to epsilon, and so that's just s over epsilon. Why did we use Laplace noise? It turns out it works in this really neat way. And if you go through the math, it pops this beautiful relationship where you have the ratio of these two probabilities equal to the e to the epsilon, which is exactly what we had earlier. And there you go. And you can walk through it yourself, right? This is the Laplace distribution. And this is the Laplace distribution for x and for y, for you can see x and for y here. And here we have e to this and over e to this. Okay, fine. I just use some simple little algebra and I wind up with this. Delta f is common on both. I can just do a little bit of algebra here. I wind up with this. Quickly and this is over all I 1 through k. That's just the one norm, so there I go, there it is. And this is in fact, right, what is this? F of y minus f of x. That's just, this whole thing reduces down to 1, and I wind up with epsilon. You can work through it if you are super motivated. And so we build our mechanism as false. Oh, by the way, if you want to see this in full detail, there's the reference for it. We build the Laplace mechanism by saying capital F sub d, right? That's our mechanism. That's the thing that's going to give us differential privacy. Is little f sub d, that's our actual query. Okay, that's what is the average. Little f sub d is what is the average. capital F sub d is what is the differentially private average. Okay, so we take the average and then we add our Laplace noise centered on 0 with the spread conditioned by S over epsilon. And there you have it. That's our scale. And you have it. So let's use S equal 1. Say we have a counting query. And epsilon equal to 0.1. That's pretty good privacy. 1 divided by a tenth is 10. And so we can get a Laplace distributed random variable from NumPy in Python as follows. So you import NumPy. For those who aren't Python aficionados, NumPy is a numerical package for Python. And the way you use it is you just import NumPy. And if you don't have NumPy in your system, I feel sorry for you. If you don't have Python in your system, I wonder what you're doing. So go get some Python, then get and install NumPy. And once you do that, you can just straight up import NumPy. And then say NumPy random, that selects all the little random number generators. We want the Laplace distributed random numbers. We set the mean equal to 0, the scale factor equal to 10. Where the 10 come from? Right, 1 divided by 0.1. And this will then generate 1. Again, if you're not Python savvy, you may wonder about these 3 little greater than symbols. This is just how you would what interaction with the prompt looks like. You would see a prompt that looks like these 3 little guys, and then you type this in. Python can be interactive, or it can be compiled. Many different ways to run Python. And we just add this to the result. Suppose we count the number of people in the data set who've tested positive for HIV, and that number is 40,150. So I play my game here, and instead of 40,150, the number I would report to you is 40,133. That's not the exact number, but it's very, very close. It's really close. It's within 0.042%, right? 42, what is that? 10,000ths of a percent. That's really close. It's close enough that I can do all the usual things I'd probably want to do with the numbers. Suppose we carefully construct a malicious query that will select a specific person, and then we count the number of people in our data set who've tested positive for HIV. Right? You see what we're doing? We build a query. We say they need this blood type and this age. They should live in this zip code. They should be this gender. Maybe a couple other things. So we're carefully picking out a particular person, and then we're counting the number of people in that data set that have age. So the result will either be 0 or 1. This is our way of tricking the system into telling us whether a particular person has been diagnosed with HIV. Well, what does differential privacy do to that? Well, it does just what you might think. It adds noise. So here's 1 plus this, and I get 31. Here's 1 plus this, and I get -6. Right? It's added some noise. And I don't know. Is it that person in the set or not? I can't tell. Maybe if I'm able to run the same query many, many times, I can start to see that there is a bias toward positive values. And as I'm more and more certain of that bias, as the probability that the bias is present increases, I am more able to say the person is present in the data set. And if that bias does not materialize, I am more able to say that person is not in the data set. So I want you to do that. So I either need to limit how many queries you can ask, or I need to cache a result, like this first one, and the next time you ask, I give you the same result. So I have to do something like that sometimes too. Whew. Let's talk about properties of differential privacy. So, the first property is sequential composition. Suppose I have a differentially private mechanism f sub 1. And suppose I have another differentially private mechanism f sub 2. And f sub 1 satisfies epsilon sub 1 differential privacy. And f sub 2 satisfies epsilon sub 2 differential privacy. You may wonder, where is the sensitivity? The sensitivity is determined by the structure of the query. Do I want the average? Do I want the count? Do I want the standard deviation? What do I want here? That determines the sensitivity. But what's not determined by that is the privacy budget, so I got to specify that. So we define a new mechanism, G, and we want to generate both results and release both results. So G is a query that might say, give me the average age and the number of residents for such and such query. Okay. So I have two things I'm going back. It turns out that G sub D satisfies epsilon 1 plus epsilon 2 differential privacy. Now, notice, if I'm giving you back two results about this, you would expect, because you're getting back more information, you would have less privacy than either one by itself. Right? When I combine the two results together, right, give me the total number of people in the state who have been diagnosed with HIV and give me their average age. So that's clearly going to have less privacy associated with it, and in fact it does, right? Both of these are numbers that are probably greater than 0, might be 0.1 or 0.2, and I add them. So this winds up being a larger number, which means slightly less privacy, okay, than either one of the two. So it's less privacy than either one of the two. It's possible that it's 0, but that's weird. You don't want that because that basically destroys all the information, right? It has to be some number. Typically, it's a number close to 0, but greater than 0. Parallel composition works a little differently. So f sub d is our mechanism that satisfies epsilon differential privacy. Suppose we construct a partition of our data set. So we take our data set D and we divide it up into a number of blocks. We partition it. Maybe we put all the men over here, all the women over here. That's one way to do it. Maybe we bin it into age ranges, or we use some other way of breaking up the data set. And then what we do is we apply f sub d to each block of our partition. So we wind up with f sub d sub 1, f of d sub 2, and so on. And we release all of those. Then that satisfies epsilon differential privacy. This epsilon is the same as this one. How is that possible? Well, before it was different because we released basically two different attributes, two different computations. Here it's the same computation, the same query for each of the blocks. And we wind up with epsilon differential privacy across the whole thing. Post-processing, something very, very common. You give me some data, right? I query your data set and I get some information back, and then I do something to it, right? So I'm going to get the data back. I'm not just going to take that data and then publish it. I'm going to do my own work with it. What if my own work reveals something that you would like to not be revealed? So again, f sub d is the mechanism that satisfies epsilon differential privacy. G is any deterministic or randomized function. So I'll pick any old function I want, and I apply G to the result. I do something with the result. Then my claim is that G of f, or f of g, however you like to think about it, it really determines down to whether you learned category theory or universal algebra first. But whatever you want, right? G applied to F is a new function that is a mechanism that satisfies epsilon differential privacy. These all come from Dwork. Whew. Well, that's a lot. Here are some final thoughts on this. Differential privacy doesn't try to keep you from doing malicious queries. It's an attempt to make malicious queries irrelevant, because I'll give you the answer to your query plus an amount of noise that makes it impossible or very unlikely or very difficult for you to reverse the result. Is it perfect privacy? No. Remember, I've got this privacy budget, and the more I turn that knob down towards 0, the more privacy I have in there, but also the less useful the results become because there's more noise in them. And, right, if the noise completely overwhelms the signal, it may not be useful at all. Remember my query where I looked for where I would get back 0 or 1, and instead I got back like 35 and -6 or something? The noise completely overwhelmed the signal. The signal was indistinguishable in the noise. So that's a problem. But if I turn it up to make my signal stronger and my noise less, then I potentially expose information I don't want to expose. So again, I'm trying to structure the queries so that I don't reveal information. I preserve privacy in the information, but I have to do that in a way that still lets people use the data set to get their work done. Bugs exist, you'll be shocked to know, in differential privacy implementations. If you're curious about what those look like, and you might be, you can have a look at this paper, Detecting Violations of Differential Privacy, and there are a lot of ways to go wrong implementing differential privacy. We'll see a few of those. But you know, lots of ways to get it wrong. I remind you of the old adage, any sufficiently advanced technology is indistinguishable from a security problem. Differential privacy fails from buggy implementations, bad parameters, weak results. You try to cache the results, but you get that wrong. A million different ways that you can get it wrong. Okay, and the paper I showed you is really neat. It's intended to build counterexamples. So counterexamples are designed to be short and human understandable, so the counterexample generator can be used. In other words, it takes your differential private mechanism and it tries to generate a counterexample that that shows that you've failed to achieve epsilon differential privacy. And that's useful. There's also approximate differential privacy. What is that? This all looks just the same except for this weird plus delta on the end. What is delta? Delta looks like a fudge factor, right? It says, okay, yeah, you're differentially private with epsilon, and then we have this delta on the end. It's something. Here you go. This allows for failure, okay? So with probability 1 minus delta, we get pure differential privacy, right? If delta is 1, 1 minus 1 is 0, so its probability is 0, we get pure differential privacy. That means we don't get it at all, so we don't want that to be true. If delta is 0, that whole term goes away. 1 minus 0 is 1, and so with probability 1, we get differential privacy, so we just straight up get it. So what you'll see is, delta is going to be something between 0 and 1. And we'd like delta to be fairly small, right? Because delta's small, this is close to 1, and we're close to differentially private. And so often we choose delta to be less than 1 over n squared, where n is the size of our data set. So that's pretty small. And it has many of the usual properties of differential privacy, but it can fail gracefully. What does that mean? What does it mean to fail gracefully in this? Well, it means that in certain cases, we allow you to just give the correct, true result. Right? So maybe when you're asking for certain results of a large data set, we know we can just give you the result. We'll just straight up give you the average, because it's not going to reveal anything special. And so we just give it to you. Okay? And so for certain things, we just give you the correct result. Other things, we apply differential privacy. And we write this as epsilon delta differential privacy. And we introduce this because we'd like differential privacy to be a little more flexible. Right? The usual default differential privacy gives us a lot of worst case stuff. And so we're always trying to add enough noise to overcome anything bad. But, sometimes we don't necessarily want that. Composing mechanisms that use epsilon differential privacy is complicated, as you might guess, because the delta values tend to add, and when they add, they get larger, and this whole thing gets smaller, and that's not what we want. There's something called Renyi differential privacy. It's another relaxed form of differential privacy, tried to make it more flexible, but still composed simply. And it's based on a special interpretation of entropy and divergence. So if you're familiar with Shannon entropy and like the Kullback-Leibler number, these are analogies to that. It's a different way of representing the entropy of a system, and correspondingly the divergence. Right? The standard divergence in Shannon entropy is the difference of two entropies, and this is sort of the same kind of thing. There's homework due on November 8th. The homework is write some Python code. Sounds easy. No. You can write this in C. You can write it in Rust if you're adventurous. You can write it in whatever language you would like. But write me a program that does the following. Take 3 command line arguments. The first one is a file name. The second is an integer index. So it's going to be 0, 1, 2. We'll see what that is in a moment. And then the third and fourth of the 3 command line arguments are a lower bound and an upper bound. And I don't care about the order of those last 2. And you should write your program so that you don't have to care either. Let me say this again. So it says 3 over here. There are really 4. And to be specific, I'm going to give you 2 bounds. A lower bound and an upper bound. And I don't care which order I give them to you in, right? The first thing will be the file name. Second thing will be the index. And then the bounds, figure it out. I want you to read a comma-separated value file of data. What a CSV is, if you don't, it's easy to look online. It's just values separated by commas, one row of your data set per line. So a row is just a series of values separated by commas. The collection of rows is the collection of lines. For the column given by the index, that's this guy, zero-based indexing. Compute and print the differentially private average and standard deviation of the data in the inclusive range given. So I tell you foo.csv as the file name. I tell you 4 is the index, which means I want the 5th field from every row. And I tell you 10 as the lower bound and 20 as the upper bound, which means I want the values of 10 or greater and 20 or less. So in that closed interval, 10, 20. Okay? And for those, I want the average and the standard deviation. Don't put anything else except to print errors if you have them, and prefix them with error so that I can detect them. The code will be automatically tested, and the test will likely generate errors. Okay? When you have questions, feel free to ask me. I'm sure you'll have lots of questions. I'll post this and an example CSV file online, and hopefully you'll be able to struggle through it. Here are the references.